Irena's not scary.
He would know.
Thank you all for joining us on the Monday morning seminar. Our speaker really doesn't need any introduction. That's our Irena Mamajanov. To give you some sense of her history, she got her undergrad in chemistry in Israel at
Hebrew University.
University, which is where Rana Kessel is now, right? Yeah.
Oh, yeah, she's...
So cool place. And I know some other people there too. And then she went on to get her PhD at Brandeis University doing solid-state NMR, which is how I got to know her, because we would meet at Origins of Life Gordon conferences, and all we'd do is talk about solid-state NMR because it's so beautiful. And so after graduating from Brandeis and doing studies related to prebiotic chemistry and solid-state NMR with Judith Hirschfeld, you went on to Georgia Tech, right, to work at Nick Hudd's sort of nascent Center for Chemical Evolution.
Exactly, yes.
And did some really interesting experiments that are very Georgia Techian, if you know Georgia Tech, is that somehow anything you do has to have a robot, and because that's Georgia Tech. So Irena found a cool way of making a robot do what she wanted it to do, and got some really cool results that are still actually, I think, very much one of the foundational experiments that the CCE did, which is this idea of automated wet-dry cyclings to drive polymerizations in ways that might do something interesting. And certainly set the foundation for what Irena's going to talk to you about today. We were fortunate that Irene got a Simons Fellowship, which allowed her to come to the Geophysical Laboratory and work in my lab, which very much enriched the environment on the second floor and the entire campus, because if you know Irena, she has a lot of life, which we love on a campus like this. And she then secured one of the first faculty positions in the nascent ELSI, which is the Earth Life Science Institute, Tokyo Institute of Technology. And so she's been sort of one of the foundational faculty members there, in particular in their Origins of Life program. So I get a chance to see Irena show me the interesting things she does, because I'm a working group member for the JSPS, and so we review it. And so I sit on the other side of the table, so I know the cool things she's doing. So then we had an opportunity when Irena was at a conference in Montana. She said, "Hey, I'm going to be in town." And I'm like, "Whoa, let's lock the date." So we could bring her without jet lag, or the jet lag's now gone, to give a talk here, and then she's going to travel back to Japan tomorrow. So without any further ado, Irena.
Thank you. Is it working? Yeah. Thank you for such a wonderful introduction. It's so nice to be here. It just feels at home, really, just like as if there were no 3.5 years or so. So I'm going to talk to you about some of the things I've done in the last 3.5 years. And I'm trying to decipher origins of life, and I'm using messy chemistry approach. And I'll tell you in a moment what it's all about. So our unofficial logo, our unofficial mission for ELSI, we are studying how planets make life. And I like to add there how planets make and sustain life. So in ELSI, you will find scientists in planetary science and biology and in chemistry actually studying how life formed on Earth, on other planets, and how life works together with geochemistry to terraform and create this beautiful and very interesting system that we have on Earth right now. So we're talking in one way or another about habitability, which is, I know, also close to this institute. And habitability is one of those very theoretical, very esoteric topics. So it's defined as measure of planets' natural ability to develop and sustain life. But really, when you start talking to scientists in different fields about it, if you talk especially to astronomy types, they would talk to you about habitable zone. And that has a lot to do with capability of a planet to have liquid water. In some cases, they would talk to you about magnetospheres that protect our Earth, at least from harmful radiation. And some would talk about plate tectonics, because it's one of the mechanisms how atmosphere and nutrients can be recycled. And then if you're just familiar people at Carnegie talking about what inside of the planet, what matters. So when you're just talking about all of those parameters, I couldn't help but wonder, aren't they all kind of Earth-centric? And then we're talking about life on other planets, it could look completely different from what we have here. So can a prebiotic chemist, in a way, contribute? So talking about another nebulous and esoteric topics, I'm trying to decipher what life is. And this is one of those phenomena who doesn't have a definition. That's as close as we get, and everybody likes to poke fun at this definition, but this is as good as we got. And in prebiotic chemistry, very largely, we have two approaches to studying the origin. And obviously, one of them is very Earth-centric. So we try to recreate biological processes in prebiotic and abiotic settings, which means we would synthesize biology building block, try to look for biological function in prebiotic environments, and try to study evolution of biological function. And then the other ways you can think about it is let's study chemistry in a very open-ended approach. Let's study prebiotic chemistry and see if it's assembled into life. So there's pluses and minuses to both approaches. Of course, we only know one example of life, so it's very reasonable to do an Earth-centric approach. However, it is unsatisfactory in some way, and I like to call it a TV paradox. So if I gave you a latest and greatest smart HD TV and asked you without giving any other information, try to figure out the origin of this technology, would you ever be able to get to cathode ray tubes? Probably not. So it just probably in this way, it would be easier to invent some sort of primitive technology and try to figure out how we get from, let's say, Flintstone TV to a cathode ray or to our television technology. Same way with life. So there's limits. Life as we know it today is very evolved, with a lot of processes evolved and changed beyond recognitions and honed and tuned. So there's so much you can learn about it by stripping our life down to simple processes. So we're trying to do it in a different, more open-ended approach called the messy chemistry. So, well, messy chemistry is about very diverse, very complex chemistry. If any of you ever tried to run a model prebiotic experiment, you would know what it is. It's qualitatively messy with a lot of processes going on, with a lot of intractable material forming. So we're trying to make a sense out of that, and it's not messy. It's not only about the system being large, complex, and intractable. It's also about sloppy biological processes. In some ways, we probably can have the same function that biology has today, but in kind of less efficient and messier way. And so CSC, this is how we go about it. So over there, and then I'm picturing, I don't know if I have, is there? Yeah. So over here, I just probably can't really decipher what it is, but what it is, it's like maybe one of the definitions of life. This is all known metabolic processes. So when you think about life, so it's some sort of subset of all possible organic chemistry that could have happened on prebiotic Earth. So the one difference between biology and prebiotic chemistry would be is the level of control and efficiency that is happening in life today. And if you're thinking about transition from non-life to life, you can think about chemical evolution process in terms of learning, while maintaining complexity, learning some sort of organization. And so the way we do it at LC, just a couple of different approaches. In one way, we study biomimetic system. We look at biologically, prebiotically plausible materials and try to mimic what biology would do. So I'll talk to you about protoenzymes and protocells. And on the other hand, we are trying to construct an evolvable chemical system in those open-ended type of chemical systems. And I'll talk about some of the work we've done in that area. So it's a lot, so what we do at LC, it's a lot about modeling, which is both experimental and some of it is in silico. And in the way we model our systems, we like to use polyester processes, polyester systems. And the reason we like it so much It's because if you're seeing over here, polyester-ester bond is very similar. It resembles a peptide bond, but it's much easier to form. So it has much more favorable thermodynamics to it. And in prebiotic literature, they talk sometimes about peptides, polyester, being precursor for peptides. For example, in some interesting work from, wow, already 40 or so years ago, when they found that ribosome, which is the mechanism of producing peptides in modern world, can also catalyze production of polyesters. Let's talk about some tangible masses that we can get in a prebiotic process. So in this particular experiment, we tried to look at a polyester library. So what we did here, we took 5 different hydroxy acids, and in very simple process, by a simple drying, we just polymerized them. And it's like something to be seen, to appreciate it, just in very simple chemistry like that. Here, we're looking at only polymerizations. There are almost no side reactions. So even theoretically, if you polymerized those 5 monomers, and let's say all we got is 20mers, you would end up with 5 to the 20th unique sequences. Of course, in real life, you don't get only 20mers, so you get an immense amount of different sequences, this combinatorial explosion. And over here, it's exemplified in the just very dense mass spec spectrum. And so far, we have identified more than 40,000 unique sequences. So what do we do with it? So we made all this met what function it could have. So we thought about using them for compartments or some sort of protocells. So the way life works is usually likes to encapsulate all its chemistry or biochemistry within a cell. And the function of a cell is to protect all the biological processes from their environment and also kind of create environment conducive to life's processes. And this is an area of a lot of research in prebiotic chemistry. Some of them, it's famous research in the area done by Shostak Lab at Harvard. So what they did there, they looked into fatty acids, and those assemble into these beautiful vesicles that are kind of very close to what life uses today. And without any biology, those vesicles can grow, they can divide, do all sorts of interesting stuff. But in some ways, this system is not very satisfying because it's only stable in a very limited range of pHs, and it's really not tolerant towards any salt concentration, which is not really descriptive of even life or prebiotic processes. So if you're watching this literature, so what's interesting about that, in a paper that came out just a couple of weeks ago in PNAS, it turns out if you add amino acids to this fatty acid system, you can dramatically increase stability of those vesicles. You get like those complex structures over there. However, there are different solutions too, and that's what we looked there at ELSI. So, and it's taking me back to one of the very old origins of life theories. It's like early 20th century. Oparin and Haldane came up with the idea of protocells being this coacervate. So what coacervate is, it's some organic polymeric material that it's a sort of colloidal particle that is present in prebiotic oceans. And this particle would house very first primitive metabolism. And at this point, the theory made a lot of sense because we're talking 1920s. Like there's like 30 years before the DNA structure was discovered. So at that point, they didn't even believe that bacteria had any genetic material in it. So that idea made a lot of sense. So what we're doing here, we're kind of like trying to think more about compartments, but more about prebiotically plausible, very similar to that, but with our polyesters. So we noticed when we dry our different polyester that I showed you in different slides, you get those like little fantastic structures. They don't have any membranes. Those are just really some colloidal structure that is floating in the solutions. And when you're looking under microscope, so what here we're looking at, like over here, we're looking at the mixture of all hydroxy acids. Here we're looking at homopolymers. And with rare exception here, you get those colloidal structures everywhere. What can those colloidal structures do? So we went and did few things to them. So over here, we're looking at those different alpha hydroxy acid polymers incorporated in very hydrophobic dye. And we're looking under a microscope, so it just suggests that those insides of those polymers are very hydrophobic. At least in one case, we were able to incorporate RNA inside those microdroplets. And so with the same system, which is polyphenylactic acids, which is more hydrophobic, interestingly, we were able to incorporate proteins. And so what's interesting about this structure, so this particular protein is fluorescent where it's folded. So it's not only we were incorporated, we absorbed the protein inside the vesicle, it's also absorbed its functional form, which gives us an idea this is an interesting milieu to try all sorts of different biological or protobiological processes in this system. So what else can we do with those messy polymers? So I've been toying around, and it was even back when I tried to work with George over here at Carnegie. Can those messy polymers become some sort of a primitive enzymes? And this is idea far from being new. So this is work done by Sidney Fox in the 60s and maybe early 70s. So what he did in his experiment, he took like certain mixtures of amino acid, heat treated it. Once again, he gets all those nice structures over here. And he actually went and tested where those can be catalytic in some reaction. And turns out that they were. So there is a good, the bad, and the ugly in this whole system. So the good, those are very interesting structures that also can divide. They can catalyze certain reactions. The bad, that the catalytic activity that he demonstrated was very marginal, and he really didn't explain it very well. And what the ugly about it, there was a lot of unsubstantiated claims in that system. For example, like lifelike behavior of this system and even consciousness. And this is something for a while, and the only reason being why nobody, it's a very interesting system, but nobody really touched it for years. Like personalities driving science, that's not so great. Well, another thing, but you keep learning about this idea, this is work that only appeared in one of the volumes edited by Sidney Fox. So this was by a person who took histidine, and he treated it and got this very heterogeneous polymers, which he called melanin, because he thought it was similar to the pigment that we have in our skin and our hair. And at that point, he writes this little paper and thinks, like, oh, I realize that it's probably not the eumelanin or anything like that, but it's very heterogeneous polymer, but maybe it's a good thing. So it means it can absorb and polymerize and catalyze a lot of different reactions. But problem is he just got interested in other things, so he never continued with this research. So I came to the field and tried thinking, can we do something more methodical in order to try to study those type of systems? And then I'm switching here. And that just because it kind of occurred to me when we're thinking about polymers, it's usually we're thinking of straight chains of different materials, but especially in those messy systems, it's probably not true. It's actually much easier to make all sorts of different architectures of the polymers. Like, for example, when we studied hydrogen cyanide polymers, and during my PhD, we took a lot of those network structures. And it's quite possible that we're getting more kind of cross-linked, networked, or branch structures when we do linear ones. So what good branch structures, what are they good for? It's actually a very fascinating system, and it's widely used in industry today. So what's nice about those polymers, they have a lot of functional group. They have intramolecular cavities. They're known for their low viscosity and high solubility. And in the industry, they would be used a lot as additive in polymer coating, supramolecular encapsulation agents, nanoparticle supports, and I don't know if they're actually used as drug delivery agents, but there's certainly a lot of research that's going into that area. So how does it help me in prebiotic chemistry? Can I actually conceptualize making an enzyme out of those things? So what is an enzyme in very broad terms? So what we know, enzyme has an active site, and this is actually an agent that participates in the mechanism of reactions, but they would be scaffolded by this folded protein, in some cases RNA. And the function of this scaffold is to protect the active site from destruction, hydrolysis from its environment. In biology right now, it's also used to very selectively bind and orient the substrate within the active site. And another function is to provide microenvironment that would be specifically tuned and would be conducive to certain reactions. So this type of idea and property is well utilized in synthetic chemistry, because there they make those structures called dendrozymes. And see the way this molecule is constructed. You have your active site, and it would be scaffolded by different layers or generations of branched polymers. In this case, it's very engineered system when you really can control the function of your complex with like different chemistry of each generation. It's not probably very relevant to prebiotic chemistry, but cousins of those dendrozymes, hyperbranch polymers, can be easily made, and then they retain a lot of the function of the dendrozymes. So what we did need, this is something actually we did together with George. So we decided, okay, so if we can make a hyperbranch polymer, and whether we can force some reactions to happen within this polymer, would they have any catalytic effect or not? So here I'm looking at a reaction that's called Kemp elimination. I know there's a lot of chemistry, but it doesn't have like any prebiotic or any relevance other than this reaction is very sensitive to its medium environment. So if you try to running this reaction in water, it proceeds very sluggishly. When you start putting it into organic solvents, the rate starts accelerating. So the idea is right now, if it's happening over here inside the polymer, would that have any effect or not? So we went ahead and synthesized a hyperbranched polyester. So it consists of citric acid, glycerol, triethanolamine. I think I forgot to mention that Kemp elimination likes to be catalyzed by base. So we threw in triethanolamine for an active site. So we synthesized this polymer. This one is quite polar, and it's quite messy. See, it's shown here. It produces a lot of different structures, which is both isomers and both different lengths of polymer. And so we also went ahead and synthesized some less polar versions of the same enzyme. So making this from adipic acid that has this apolar moiety and metal succinic acid. And just that George happened to have it for different reasons sitting on the shelf. And so we've synthesized these polymers, and the real test is to see whether they have any catalytic activity. So over here, we're looking at monomeric triethanolamine catalyzing the Kemp elimination, and there is some rate of the reaction. You throw in citric acid, glycerol, and triethanolamine polymer, it works a little better. But with metal succinic acid glycerol system, you get acceleration of about factor of 3. And of course, it's maybe nothing to write home about when you're thinking about enzymes, but just remember those guys are 7, 8 monomers long. And so the way we did this analysis, so we never isolated any active species after all this mixture of polymers we got. So inside this mixture, there might be some neutral species and there might be very catalytic species. So I think it's very encouraging result. We published a couple of years ago. So is there something more interesting that we can do? So and here I was thought what would be more geologically, prebiotically relevant system I can do with this Hyperbranch platform. Now I start thinking, we're talking a lot about black smokers, about ideas of iron, sulfur, or other metal sulfide protoenzymes catalyzing all sorts of interesting prebiotic chemistry. So this was my idea. Let's create a protoenzyme. And by protoenzyme, let's have a scaffold, and let's see it support metal sulfide nanoparticles. So in this case, we started working with commercially available Hyperbranch polymer, polyethyleneamine, which is also a very nice chelator. And it's a super simple process. So what you do here in order to create your metal sulfide, and we played with zinc and cobalt just to begin with. We took solution of this polymer, we added zinc or cobalt chloride solution, and following that, we added sodium sulfide solution. So what happens here? So when you add without any polymer, you take your zinc chloride and add sodium sulfide, you get this precipitate. And if this didn't happen, you continue having clear solution when you have polymer present. And it's also true for cobalt sulfide here. And when you look on the TEM, you saw those look like very interesting nanoparticles. When you zoom in, you see that those are about 10 nanometers in diameter. And another interesting, and another interesting property of it, so you let this sample sit for 2 weeks or so, you get some aggregation, but visually you still get a solution without any precipitate. And those aggregated particles are not terribly big. Those right now about 50 nanometers. Well, polyethyleneamine commercial sample, it's great, but I would have had a hard time convincing any prebiotic chemist that they would have anything to do with prebiotic earth. So I would started to see, let's start working with our favorite polyesters. And for the longest time, it just didn't work. I wouldn't get anything, and I just couldn't figure out for the hell of me why not. And so we know that this has a lot of, this polymer, polyethylene, has a lot of functional group. It can coordinate a lot of metals. But it seems like my polymer has a lot of functional group as well. So what was wrong? So and at this point, I went for a lot of money. I bought those dendrimers from Sigma Aldrich. And those are both polyester dendrimers. And the difference here, this one is terminated by carboxylic acid group, and this is terminated by alcohol groups. And it just, when you run the test, it turns out they don't really coordinate any metals, which was kind of surprising. However, when we try to prepare our polyesters in the presence of cobalt or zinc sulfide, we're getting incorporation, coordination on the same order as we would with, almost on the same order, almost as well as we get with commercial sample. And it probably shouldn't have surprised me that much, because this is another paper that we did with George. And so this is like our first time playing with Hyperbranch polyesters. So we took glycerol and citric acid in 2-to-1 proportions, and we polymerized it, and we just got those moieties that had twice as much glycerol and citric acid. But then we went and threw in a lot of divalent cations. And basically, in every case with divalent cations, we got very different structures. We got glycerol-poor strands of the polymer. And this is what was happening is because citric acid is a great chelator. So I think what would happen, it would chelate with the different cations over there, and then you start polymerizing. You're not polymerizing free citric acid. You start polymerizing those complexes, which would be less reactive towards polyesterification. And so you would need more of them to make a polymer. So and just by adding this metal, you would get completely different structure of a polymer that was kind of interesting. But here's the real test. So this is another assay reaction testing the photocatalytic activity of zinc sulfide nanoparticle supported by hyperbranch polymer. In this case, we were just looking at the dye and the degradation of it. So if you took this dye and put it into UV light and tried to degrade, pretty much nothing happens. So when you throw in together with titanium oxide nanoparticles, which are commercial photosensitizer, you get like much faster degradation, and it seems to be working much better with both our commercial polyethyleneamine support and our polyester support. That probably is different has to do with the fact that we're making smaller nanoparticles than titanium oxide. So another score. So after I talked about function, well, let's move on and see what is, I think, is a real frontier of origins of light research. Let's think about how we would go around and make a chemical system capable of Darwinian evolution, which is like the best definition of life, what we know. And what does it mean? We would need to have a system that is selective. We need to have a system that can replicate itself in some ways, and it also needs to replicate itself with mistakes. So that's how a mechanism, how Darwinian evolution happens. And we should be able to replicate the mistakes as well. And there is one theory of origin of life that actually incorporates all those properties, and that's why I think it's been so popular. And this idea, it's called RNA World. So what RNA World is, it's, let's say, you have in your prebiotic soup and some sort of prebiotic environment, you have nucleotide, the monomers of RNA. And you probably, by some process, you polymerize some sort of the templates, a short piece of RNA. And that what you would do, you can selectively pair those nucleotides with a template. Then you need to invoke some sort of polymerization. Let's say when they just first things you assemble this complex, then you polymerize it. And then there's also, you can think of mismatches sometimes happening. So you can have selective binding to template. You theoretically can get replication, and you can get mismatches. So there's some few issues with this idea. First of all, it's just starting with nucleotides. And just for not chemists amongst us, this monomer is actually very complex. So it consists of this nitrogenous base. It consists of sugar. It consists of phosphate. We probably know how to make nucleobases. We probably know how to make sugars and prebiotic contents. There must have been some phosphate around somewhere, but we really don't know how to make this molecule. There was some work that coming from John Sutherland lab. And so this is like, wow, it's already 10 years older. So, but that just like one of those paradigm shifting, maybe, works in origins of life. So what happens with this? This work received a lot of criticisms. This is very, although they do make in seemingly one part process, they do make a nucleotide. But it's actually a very engineered process, and probably wouldn't work without any skilled chemist adding needed materials at the needed time. And well, they use like 1 molar phosphate or something. That's probably many would say it's not really plausible prebiotically. Well, there are more problems with RNA words. Nucleotide coupling, that's another not thermodynamically favorable process. And there, like here and there are some ideas of how to polymerize RNA or nucleotides abiotically, but those processes usually yield, well, they are very low yield, and they also yield very short polymers. And that's another problem. So it has to do with coupling of monomers to an RNA strand. It turns out, let's say you were able to synthesize your template and you synthesize your duplicate. But right now, it's actually this a complementary strand of RNA would be more tightly bound to its template than any free nucleotides would. So we need to think about how would you think about strand separation. So there's a lot of issues with this theory, and well, we still need to be convinced whether those issues are conceptual or just more research needed. So we decided to think about how would we go in very much simpler, much before RNA, how we would go and construct this chemical system. And it's a very tall order. So we started to see how we can go about separately for now, about selection, about replication, and heredity. So selection, it's probably one of the easiest concepts to grasp, because after all, chemistry, it's not free for all, they're all, they're not that any chemical would react with any other. And there's some studies there in prebiotic chemistry talking about selectivity. This is an example that comes from Steve Benner's work. So he is looking at the process of making sugars from formaldehyde. And so the idea there is, well, we've been told a lot of times that you polymerize formaldehyde, you can make all sorts of different sugars. But what we don't hear that often, so the most of the product there would be this intractable polymeric tar material. However, what he learned, when you throw in some borate minerals in there, you don't form the tarry polymer anymore, but you can selectively stabilize short sugars, which was like so another piece of research that was a lot talked about in Prebiotic World. Talking about Steve Benner, he likes to do so, like something to do with chemical evolution. So he likes to say, so if you take organic molecules, give them some sort of energy, so throw them together, and they would devolve into complex mixture, asphalts, tars, or something like that are better suited for paving roads than supported Darwinian evolution. Well, he's probably right, like in that sense. So when you talk, like you're talking about your normal prebiotic model environments, you would talk about HCN polymers that would make this tar. So we all can know that Miller-Urey experiment produced amino acid. What we don't talk really a lot about, that they mostly produce this black tar. And like here I'm showing this picture of titanium by Cassini-Huygens, and many believe that this black material is tar. So yeah, so probably Steve was right. Like once you get, when your prebiotic system gets to the point to some sort of equilibrium forming those materials, it's not useful for any sort of chemical evolution anymore. So can we do something about it? So you can see right now I'm really enamored with my Hyperbranch polymer. And it turns out that in that system, the formation of tar has been described much better than any other type of polymerizations. So what they noticed and actually quantified a lot, when you start polymerizing your, trying to make your Hyperbranch polymers, you take multifunctional monomers, you polymerize them, get those nice branch polymers, but usually what would happen is very defined molecular weight, you get gelled products. So like very drastically at this point, the system would just change a lot of properties like solubility, viscosity. So is there any prebiotic process I could think of which just kind of could keep my polymers at this branch phase and just prevent formation of this network polymer that's associated with gelated product, is gelation. So what I thought about doing, once again, citric acid glycerol polymer as usual, and I subjected that to wetting drying cycle. So it's kind of recursive polymerization. Whether you dry down, you polymerize some, that you put your polymers into water phase, and that would degrade some. And the idea was here you would avoid gelation, but like very rudimentary control over the molecular weight of this polymer. And turns out it works like pretty well. So when you continuously dry this polymer, it gets gelated after 48 hours of drying. And with cycled product, it just actually remains soluble for 32 days or 8 cycles. And what's another like, interesting point, the structure of the polymer is very different according to the different slew of different analysis we've done. So over here, you kind of get more network, more cross-linked polymer, while when you cycle, you would get more branching. So that's kind of a couple of our ideas on selectivity. What about replication? So it turns out it just comes down to autocatalysis. And I just, as a chemist, you learn that like autocatalytic reaction is a single reaction that would be autocatalytic if it produces its own catalyst. And there are very few of those known in chemistry. However, it turns out that autocatalytic set, like this is like complex, like big network that can amplify its own production. Those are actually turn out to be very much easier to achieve. And this is like I want to talk about work done of one of my colleagues, Nathaniel Virgo, who is doing a lot of artificial chemistry. So here's like he was trying to do to study the autocatalysis in those like very virtual, very abstract polymerization technique. So he set up this polymerization process. You have monomer A, and you allow all sorts of reaction. You can take two A's and couple them. So this monomer A can couple to, can react with like all sorts of different oligomers to elongate itself. And next thing he did, like just the system with no constraints or anything like that, he just analyzed the kinetics of this reaction with like all those parameter arbitrary and distribution of products. And over here, in the most polymerization you will exact, you get like this distribution with like some short monomers and with longer tailing off. So next things we did here, just let's say here, we disallow the formation, the coupling of two monomers. So, and what happens in the system, so when you start analyzing its kinetics, you get like production of nothing that's what we called an induction delay. And after some period of time, like reaction takes off. And this is like type of kinetic we get if we get first order autocatalytic kinetic. And this is like this type of kinetic is very characteristic of autocatalysis. So if we were looking in real world, so this type of process is very similar to Formose reaction we talked about earlier. Because in Formose reaction, is you take formaldehyde, it's very hard to couple two formaldehydes together. But once you reach that stage, the reaction takes off. Then Nathaniel tried to do something very weird. Let's like disallow different reactions. So in this particular set, you can't form any A7 species anymore. And even more crazily, okay, none of the multiples of 3 are right now allowed. And when he analyzed the kinetics, so once again, you get an induction delay, and then reaction takes off with much more complex kinetics. So his ideas was few, so his take-home messages. So first of all, autocatalysis seems to be very common. And another take-home message was, but in order for it to be common, you need to start with sufficiently large chemical system. So what we're doing here, we took a large chemical system and we're taking away reaction, and the system seems to be compensating and forming autocatalytic cycles. However, if let's say you have a system of 2 reactions, you take one off, probably the system doesn't have the capability to compensate. Well, another thing, so having like that in mind, that autocatalytic sets are common, we tried to run this crazy experiment in the lab, and Jim over there deserves most of the credit for it. So what we did in this case, we took very simple aqueous reaction. Like over here, we have very simple, mostly inorganic nitrogen sources, very simple organic, usually 1 or 2 carbon sources, and we have, like in some cases, we added some cations. And like probably most interesting about the system, we let it sit for about a year. And so here I'm showing you a video. So we're taking a snapshot of the system, what's it doing every few weeks or so. So you're saying, especially when you have transition metals in the system, you would get some color changes. But when you keep watching, see, if you saw over here, there was a couple of reactions sitting there doing nothing. Here, there's another one going. And just after, like in this case, I think 6 months and 8 months, like all of a sudden the reaction changed color. So what do we think is happening? So analytics, unfortunately, in this complex system with a lot of chemistry is difficult. So for now, we're just like few facts that we know, but we don't know exactly what's causing this color change. We know that, for example, having this transition metal cocktail salt is important. We know that it's probably this whole chemistry associated with some variation of aqueous HCN chemistry. So what actually convinced me with this system is when you take some aliquot, small aliquot out of like this system that turned black and seed it into a fresh solution, this color change happens much faster. So it was very indicative of autocatalytic process. But work still very much in progress. Analytics and all those messy systems is real bottleneck. So it's just an ambient light in the lab, yes. Oh, okay. So, and then just finally, like probably one of the most difficult ideas to grasp is heredity, which is not based on any type of RNA. And so this is like right now, this is like very theoretical. There's a couple of ideas I'm throwing out of there. So one of the very interesting processes, and this is the way in industry how they would go and synthesize chemical sensors, is this idea of molecular imprinting. And the way it works here, you have a certain template. You self-assemble it together with some sort of functional monomers. You then invoke somehow polymerization. So now there is a polymer forming around that template. At some point, you kind of go and remove the template, and what you're left with is this polymer with, it could be a very specific binding site or molecularly imprinted for this specific template. And I just haven't given a thought, as this process seems to be very industrial, until like this paper appeared on Archive, and it's written by Eric Drexler, who is one of the fathers of nanotechnology field. And if one thing I learned from Nick Hudd is like every scientist is a closeted origins of life scientist. So he had this idea that in peptide world, you can have molecularly imprinted replication of peptides. And so to think about this idea, just once again, you might have peptide template, you self-assemble it with kind of small amino acid. Once again, it always seems to come back to drying and wetting cycle. Well, drying is your polymerization. When you wet, when you move template, and theoretically, you would get imprinted material. So this is something we're trying to work out right now, but it's just in the idea level for so far. So I think I would conclude now with few thoughts. So I think we have, like, there's a lot there to learn if we're stepping away from trying to synthesize biological structure in prebiotic world. So we're just going to be more open-minded, and it gives you, would probably, hopefully give us a lot of universal life principle, and maybe give us better ideas of more universal biosignatures that are not based on our life. And so messy chemistry systems are very interesting. They might be, in some cases, might be necessary for origins of life, but this is the system which we should be studying in the context of origins of life. And that's just one bottleneck is well, analytical chemistry becomes very, very difficult. So more people, newer ideas are needed over there. And with that, I would like to thank all those wonderful people at ELSI who helped me with all those projects, and thank you for your attention.